Join me for the adventure that awaits inside the box.
Greetings, adventurers. Today's adventure is generating clocks in Vivado. Back in the VGA project, I mentioned that it was important not to make clocks with the logic. The reason being that the routing can generate different lengths, so the clocks do not get to all your logic at the same time, and as a result, you can get glitches and projects that just won't work. You'll wonder why. It'll be really subtle. When am I going to learn to type after so many years? Yep, RTL is fine. And we're not going to add the files. I'm going to do that in the editor. Do we need... Nope, no constraints yet. I'll add that as well. The default part is the... Nope, it's the Zybo. Let's see... No, what am I doing? Zinc. Where is it? The board already. Boards. Ah! One of these times I'll remember the correct board. There it is, the Zybel. That's what I have. Okay, now we're going to make a project. Oh, no, we're not doing Verilog. We're doing VHDL. Yep. Okay. Simulator mixed is fine because some of the IPs will use Verilog models. You need that as mixed for that to work correctly when you simulate. But we're not really going to do much for simulate. Okay, we need to create a source though. Create a design source. Oops, nope. I want to create a file. And clocking. Not VHD works for me. Yeah, we can finish. No. The name for the implementation, or the behavioral as it's called. Implementation. Yes, I do that myself. And now we load a source. Oh yeah, all these things I don't use most of the time. Okay. We not need them. Well, I'll leave the math. Okay, we don't need the Unisim. And okay, ports. Okay, I better add that constraint because I want the add a constraint source. Add create constraints. Next, add a file. I gotta get the Zybo board. There's a good one to get it from. Zybo hello. Do I have it in here? No, I don't see constraints. Oh, I'll get it from the C64 project. I know that one has it. Yeah, it's the board file for the Zybo that I'm importing the constraints for. Copy to the project. Yes, always copy it because you might want to change it, as I'm just about to do, because I want an LED and I want, yeah, an LED so that I can flash the clock that we generate. And yes, you need the system clock. That's this one, clock 125. You can change the name to it, but I'm going to leave it. Switches, buttons, LEDs. Turn them on. Okay. And I'm not using the VGA in this project. I am doing it in the VIC chip that I'm doing to make a C64 simulation. That'll come. It's a lot of stuff to make and debug. Okay, we can save that. Okay, and it's just called LED. That's perfectly fine. Okay, and we have to put that in our entity and their outputs. So LED. Now I gotta remember if I need to. Yeah, because these are, no, that's right. They're just standard logic vectors 3 to 0. And that will give me the LEDs. Oh, yeah, right. What? Oh, yeah, okay, I guess it wants the semicolon. Normally that box. Nope. I was right the first time, wasn't it? No. What are you complaining about? Oh. Output. Okay. So at this point we just got the LED. We need the clock. Well, before we do that, we have to actually create a clock. So for that, we go to the IP catalog. Where is it? Here it is. And we need to add FPGA features, clocking wizard. There you go. Yeah, you create this, and then you have to add it. So you double click it, and now it's going to ask you to make a clock component. And we only need the first one, system clock. There it is. So now we go to clocking options. MMCM, yes. Input clock. Okay, so that's set. We don't have to do anything with that. Frequency synthesis, alignment, balanced. Those are the normal ways to handle it. There's some other options as well, but we don't need them for this. Output clock. This is where things matter. Okay, we want a multiple that's easily to divide so we can make a suitable rate. We can make, this is a megahertz clock. Well, create a 1 megahertz. That will, okay. I can do the math. That's, 1048. Oops, 048. 576, but we ain't gonna get that for sure. Oh, yeah, see, it's complaining. Too many decimals. Get it until it don't complain. Oh, is it too slow? 1 megahertz is too slow. Okay, we can't do that. Is it 8? 8 is fine, right? Yeah. Okay. Okay, so it's 8192 megahertz. 0.192. This will, or that should be fine. I could also do it with just 8 or just 10. I don't want to use divide by 2s. They're a little easier. Now, we'll even it up. So, okay, so we're going to have a single clock with 8 megahertz. Oh, I have to rename it. I don't have to rename it, but it'll just help to remember what it is. Alright. 8 megahertz clock. We don't care about that so much. And these are all good. You don't want to touch them anyways once you've set the things here and renamed your ports. As you see, it's based on the input. Updates will override, so you don't want to do that. It's going to use the system clock as input and give us our 8 megahertz as output. Did I check that the phase was 50%? Yeah. Okay. Now it makes a clock. This will be the important thing, the instantiation template. So we generate. And it takes a few moments to generate the bits. Once it's finished, we go to IP sources. And those haven't been set up yet. Oh, yes it has. We want the template. So we load the template. And it's a VHD file. It has 2 parts we need. We need this component part, which is defaultly named clockwiz 0, which you have to keep the same. So we take that. Notice it's read-only, so we'll have to copy it over. So that goes in. The components go in architecture declaration. There it is. Then we also have to map it. So we have to copy this part. And that also goes, this time it goes in the body, or the implementation part. Yeah, we don't need to call it your instance name. We'll call it something sensible like clock. Oh, I don't know, clock. And now we have to define the signals to take our pins. So we need a signal for the clock. I need another one for the reset input. And the last one for the locked output. Okay, and I'm not worried about resets, so we're going to make sure it just stays to 0. There's a, okay. Oh, yes, the clock input, which reminds me I didn't set that pin. I need it. I need 125. That's an input, standard logic. And there we go. Right, because it needs its input reference. Oh, there it is. That's an output, so you can just leave it disconnected. And the 8 AM clock is okay. So now we can write a process. So we want to get 8 megahertz down to like about 8 hertz. So pardon me as I drink some coffee. Okay, 8. Okay, so we're going to have to divide by quite a bit. So we're going to need a counter. Good thing I left the math in there. And you're an unsigned. Ooh, learned to type already, Brian. Okay, unsigned. Yeah, you need to count to about, well, at least 8,000. That'll get it down to 8 kilohertz. So we even got to go more than that. We got to count to about like 8 million. Get like 1 hertz. So what 8 million would be, we need enough bits to count that high. So 1048576, that's 20. So we need 4 more, or double the power. So that'd be 21 is 2 meg, 22 is 4, 23 will be 8, and I may as well go, we can count to 16 meg. So there it is. And I better set a constant, so otherwise this is going to be a pain in the keister. Constant. I'm not typing that twice. Unsigned 24-bit. Dry. Don't repeat yourself. So I'm going to keep typing this unsigned? No. I'm going to make a subtype and then use it the multiple times that I need it. Now I can use the 2 integer, 2 unsigned actually. And it's going to be the 8 million divider. And you have to specify the length on these conversions, so 24 bits. And that will give me a constant that I can compare to on the counter. Oh yeah, we should initialize it to 0. 0. No, let's use hex. That's 4, 8, 12, 16, 20, 24. Yeah, hex is much more compact for that one. Just set it to 0. Okay, so we need a process to deal with that. Oh, haha. If I'm going to divide, I better make that 4 million. Right, duty cycle. There's duty cycle in there, Hills. And this is our this is the clock we're going to generate. It's just a divide down so I can have the LED come on and off at a reasonable rate. So we're not dividing the system clock. We're going to divide that 8 megahertz even clock. We're going to divide it by 4 million. So it's going to give us 2 hertz, which on each half is going to end up being 1 hertz once a second. So it'll be it'll pulse back from on to on every second. It'll be pulsing between on and off every half second. So now we need the counter, which is a process that is sensitive to the input clock. Nope, the 8 meg clock. So that's the clock 8M. Learn to type, Brian. After so many years, I still don't type right. It's a lot of years. Okay, we called it CLK8M. Alright, is begin, end, process, count. You'll notice that I try to, what are you complaining about? Oh, okay, well then I have to modify it to not be a duplication. Okay, I don't want that counting. Divider, that'll work. I haven't used anything of that language yet, so that'll be a good choice. Okay. We have the rising edge of the clock. We're now, okay, so that's when the clock goes high, transitions to high. We want to count, so we want to check the count. So, oh yeah, we need a signal. Variable, rather. Add to our counter, and then we compare it to the max. Count 8M. Oh. I already got that. Okay, that's the constant. Count is the signal. And this is where we do it. So we'll reset to 0 and right. Those unsigned constants don't like regular numbers. You have to actually spell them out with a binary or a hex. Unless you want a big long line of typecasts. So I used the hex. It's been hexed. Okay, so we set the counter to 0 and we have to toggle our slow clock. Type, Brian, type properly. It's going to take long enough for this video without typing errors everywhere. Alright, that should do the trick. So now we have our clock. Now let's oh, here we go. That should be, let's save. That should do it. Let's run that bug. Let's run the puppy. And I can't see the Zybo because I don't have funky picture hardware. So I'm going to generate the Bitstream, which is going to do a compile. And, you know, I'll probably edit out the compile because it's long. Okay, it's got to compile it, and it's going to implement it, route it, simplify it, generate the bitstream. And when that's all done, it'll generate a bitstream that I can set to the board in Hardware Manager. Synthing the design. Maybe I'll take the video of the board pulsing the LED and I'll overlay it. It's going to be a pain to do because video editing's quite a pain when OpenShot likes to crash every second time you do something. And every millionth time you do, or maybe thousandth, it wants to corrupt the file, and you got to start over again. Corrupt meaning it corrupts the save. Yeah, been here, done it. Not fun. Writing the bitstream. That's the important one. Okay, the Hardware Manager. Open a target, which is desirable. It'll connect. Program. Sending. And what did I do wrong? I don't have anything. I don't have any LED. Slow clock, not slow clock. You're not on. Why isn't the LED coming on? Haha! This is why I don't like doing this stuff on recordings. What is the problem? Rising edge of the 8 meg clock. Is that? Yes. Are we supplying the... Are we stuck in a reset? No. Is it active low? Maybe? Is it active? Maybe it's active high. No. Is that it? Shouldn't be. It could be. Let's... Oh, nope, that's not it. That's not it. Cancel. I just found it. No, it's not that. Okay, I'm putting it in the variable, as we can see. You know what I didn't do? I didn't store the variable back to the signal. So, here's what has to happen. Count, assigned to signal assigned, value of current. There. That changes everything. And now we have to compile it again. But I'm going to leave this in the video. No one ever gets code right the very first time. It just doesn't happen. Especially when the camera's rolling. That guarantees something's going to go wrong. Coffee. Yeah, we gotta wait again. What should I talk about in the meantime? I have another video where what I'm trying to work on, where I talk to the sound chip and have it identify over the I2C. I have the sequencing graph that shows the progress when you have a positive acknowledgement versus a negative acknowledgement. Of course, that is meaningless unless you know I2C, which I will have to describe for that video to make sense. And then I have the overall project of doing a Commodore 64 simulation. It's not going to be exact. It's not meant to compete with emulators. It's meant to do the main things that you expect a Commodore 64 to be able to do. Like have a VIC chip screen, colors, the 16 colors that you know. It should do raster interrupts. But maybe some of the funky VIC modes like FLI and stuff, that's probably not going to work. I probably won't even do the 6502 decimal mode because it's kind of a pain. And forget the undocumented instructions. They're not going to be there either. And that's basically what I mean by a simulated 64. Okay, you have to take my word for it, but I'll probably go into the editor and record the flashing LED. It is flashing. It's on a half cyclical. So it's every half second it's transitioning, and it's going from 1 to 1 over every second. And it's going 1 to 0 every half second. So it's changing every half second, but going full cycle every 1 second, as expected. And with this, we've made a clock using the IP Clock Wizard. So thank you for watching, and until next time.